Good afternoon and welcome to Techtalk. My name is Karen Taylor and I am the Director of Technical Training at Acme Packet. Today I will be your moderator for this presentation. In this webinar, we will introduce IPv6 from a theory perspective, as well as discuss how to implement IPv6 on the NetNet Session Director. Consequently, this technical session is targeted towards our customers who are system operators and network engineers. Our main goal for every webinar we offer is to pass on our experiences with signaling protocols, interoperability requirements, and network topologies on to you. Before we get into the presentation, I'll go over a few points around logistics, starting with the agenda. For today's topic, we'll start with a discussion on the drivers and benefits to implementing IPv6. We will then discuss the IPv6 header format and addressing. We'll discuss how SIP works with IPv6, as well as IPv6 on the NetNet Session Director. Towards the end of the hour, we'll point out some key takeaways and give you some resources for gaining more information. The lecture portion of this presentation will last 50 minutes, followed by 10 minutes for questions and answers. While we will mute all participants' phone lines for the duration of the presentation, at any time during the presentation, you can use the instant message text field of the GoToWebinar chat questions window to ask a question. We will answer all questions through the chat function, and we'll also answer some questions live during the end of the call. Following the presentation, you'll receive an evaluation form via email, and we would really appreciate your feedback in order to enhance future Tech Talks. You will also receive the presentation materials, a link to the presentation materials via email following the presentation. Acme Packet Session Delivery Networks encompass 8 product categories that enable devices to communicate across the IP transport layer to applications and services in your network. Today, we will be focusing on how to control sessions at the border of the network. With that, I'd like to introduce Mayor Brosh, who is a course developer and technical trainer at Acme Packet. Mayor will be leading you through the rest of the presentation. Mayor?
Thank you, Karen, and I'm happy to have all of you here. According to geography, it's either good morning to you, or good afternoon, or good evening. Let's begin. When we look at the media or we browse the internet, we see lots and lots of opinions about when and how and where is IPv6 going to be implemented. And there are many opinions expressed by different experts, like the one that you see here, that IPv6 is due for wide deployment in 2012. Other experts might say, that IPv6 doomsday won't hit in 2012. So we don't really know when exactly it's going to take place. However, it's going to be a long transitional period where we'll see a lot of coexistence between IPv4 and IPv6. The main driver for the need of IPv6 is the well-known IPv4 address starvation. We have many new categories of constant-on routable devices, like automotive gadgets and appliances and monitoring devices, and they will all be globally routable. That means that an average user will need to have several IP addresses. As the things are now, some of the US universities and corporations have larger address space than some countries. Things like this were over the years mitigated by netting, which is not ideal, and it has some bad impacts. For the e-economy, we really need global internet accessibility, and this is something that was to a great extent hindered by the net. So the need for the IPv6 is synonymous to the need for clean global routing model. There is also a need to address assignment management, which is better than we saw during the era of IPv4, which was flexible, but not to the point where we could eliminate ranges of addresses that are not allocatable and are not usable. So there is a lot of waste in IPv4 addresses. There is also no inherent security in IPv4, and security more than ever is required as part of the IP. The benefits of IPv6 are first and foremost huge address space, which means that there is room for many levels of structured hierarchy and routing aggregation. In IPv6, it is easy to address auto-configuration, and it is easier to manage address allocation and delegation. The header format is streamlined, it's simpler, it's cleaner, and it contains some functionalities that we don't know in the IPv4, like, for instance, flow identification. There is better support for options and extensions in IPv6 compared to IPv4. And security is actually mandated. So IPsec is part of the IPv6 architecture. The addresses in IPv6 are 128 bits addresses, which we all know enables us to create lots and lots of addresses. But just to give you a slight feeling about how huge this address space is, consider a particle, a dust particle compared to the globe. And by a simple calculation, you can find out that as many as 2 followed by 32 zeros particles are in the globe. And if you evaluate 2 to the power of 128, you will find out that about 3 followed by 38 zeros is the number of IP addresses. So actually, you can assign an IP address to each and every dust particle on the globe. And still, you end up with lots and lots of unused addresses. So it actually makes you think that it can cover all the dust particles of the whole solar system, or maybe more. But we only need to cover part of our globe. So let's take a look at some general characteristics of IPv6 generically. First of all, you can see at some of the RFCs that were written over the years regarding IPv6. One of which is the 2460, which is the basic IPv6 specification. As you can see, it actually obsoletes an older one. So 2460 is the current IPv6 specification, which is also augmented by the green ones that you see here that are RFCs that update the basic RFC. So the 2460 specifies the IPv6, talks a lot about the header format and the options and routing and whatnot. Another RFC which is worth mentioning is the 4291, which is about the address architecture. And this RFC discusses the various types of addresses, their format, their usage, and so on. Other RFCs talk about ICMP version 6, auto-configuration, neighbor discovery, which is the equivalent of IPv4 ARP, and so on. Most of the RFCs are extremely well written. They are not too long, and one can very easily familiarize himself on IPv6 by going over the RFCs. Looking at the addresses that are conforming to RFC 4291, there are three types of addresses. The first type is called the unicast address, which is an identifier of a single interface. When a packet is sent to a unicast address, it is delivered to the interface identified by the address. So this is simply A sends a message or an IP packet to B. The next type is called the anycast address, and the address format is the same as the unicast address. The difference is the way it is processed and interpreted. So the anycast address, by definition, is an identifier for a set of interfaces. A packet sent to an anycast address is delivered to one of the interfaces identified by that address, which is normally the nearest one according to the routing protocol's measure of distance. So the model would be like this. If E, B, C, and D are an anycast group, and A sends a packet through the routing cloud to that group, only one of the stations or one of the hosts will receive that packet, and that will normally be the one which is topologically closest to the router. The multicast address is an identifier for a set of interface, exactly like the anycast address, but a packet that is sent to a multicast address is delivered to all interfaces identified by that address. And as you can see, these are all the types, and there is no broadcast in IPv6, just these three types. Let's take a look at addresses and prefixes. The notation of the IPv6 address is 8 colon-separated 16-bit hex numbers, case insensitive, and leading zeros can be omitted. And here is a basic example. When you encounter a string of zeros, consecutive zeros within the IP address, something like you can see here, you can replace this occurrence of zeros by colon. So if we look at this example, FE80, zeros, and then the other hex values, you can write this same address in this form. FE80, colon, this is instead of the consecutive zeros, and then the rest of the hex values, and as you can see, the leading zero here has been omitted. There is also the notion of loopback address, which is very simple. It's many zeros followed by a single one, which can be abbreviated to colon 1. There is also a notion of unspecified address, which is all zeros. And again, following the same rules, it can be abbreviated to colon. Let's see how a unicast address looks like. And a unicast address can be of two flavors. There could be a global unicast address, which is normally allocated by the IANA, which is the numbering authority. And it looks like this. You have 48 bits that start with 001, which we call site ID or global routing prefix. So this is actually something that will be allocated on a global basis. Then you can see 16 bits, which identify a subnet, and the rest, 64 bits, are considered the interface ID, which are in a format defined as EUI64 format, which is a fairly simple one. Here is an example, like 2001, 0DB80, another 0. The subnet is CD30, and the interface ID is randomly, I chose it as a random value 1, 2, 3, 4, 5, 6, 7, etc. So this is considered a global unicast address, meaning that routers will actually process this type of address and route it. The other type of a unicast address is called a link local, which is not routable, but it is a very valid unicast address within a link. That means this is actually the addressing scheme used by neighbors that are attached to the same link. How do you identify an address like this? It has these 10 bits that you can see, and then more zeros, and again 64 bits, which are the interface ID. And the example would be FE80, which is always the prefix of the link local address, followed by zeros, which are abbreviated to : and then the 64-bit interface ID. Now, the interface ID can be obtained either using DHCP-v6, or they can be statically or manually set. And in many cases, it's recommended that the interface ID will be somehow derived from the MAC address. We then have the multicast address. The multicast address is identified by 8 ones, and then 4 bits of flags, and then 4 bits that define a number that identifies a scope, which means that the IPv6 addresses have scope. The remaining 112 bits is simply the multicast group ID. Here are some examples. We have the local scope, or the link local scope, and as you can see, there is an address already preset, which is FF02, many zeros, ending with 1, which means all nodes on a link. So all nodes on the link are actually a multicast group, and each and every one of them has this IPv6 address assigned to its interface. I'm sorry. Same address that ends with a 2 will match all the routers that are on the link. And then there is a very important multicast address, which has at its end FF00 and then more 0, or it can define a range that ends at FF:FFFF. So this is a range of addresses, which again are multicast addresses, and they are called solicited node addresses. And these are the key addresses that are behind the mechanism which replaces the ARP. There is no ARP in IPv6, only in IPv4. However, we still need to find out the MAC address of a host to which we want to send a packet. So the solicited node address is really the key. When we go to the bigger scope, which is called site local scope, we have more examples like FF05, where the 5 is actually a different value for the scope field. If it ends with 2, we mean all the routers in the site. If it ends with 1 and then 3, it's all DHCP servers in the site, and so on. These are just examples. We then have multicast addresses which are valid for all scopes. So they are considered like variable scope. They are normally allocated globally by the IANA. As an example, FF0, and it doesn't matter what follows the 0, if the address ends with 101, that will actually address all the NTP servers. If you look at the note, the note tells you that many of the permanently assigned addresses by IANA are valid within any scope. We have two types of nodes in IPv6. A node which is a router, and a node which is not a router, and it's called a host. And the RFC actually stipulates there is some required addresses. And the node is required to recognize the following addresses as identifying itself. Obviously, every node has its loopback address. Every node has to have its link local address for each interface. That means neighbors can talk to each other using these addresses. Every node has to have all configured unicast and anycast addresses, all corresponding solicited node addresses. This is for enabling the address resolution or the MAC address resolution. If a node belongs to a multicast group, then all nodes multicast. A correction. Unconditionally, the multicast address of all nodes. And then multicast addresses of all groups the node belongs to. If the node happens to be a router, then the subnet router anycast addresses need to be assigned, and the all routers multicast addresses need to be assigned. What you see here is the good old IPv4 packet, which has a fixed portion of 20 bytes. And if you look at the source and destination addresses, there are 32 bits. We have options, and then we have a variable chunk of data. This is how the IPv6 header will look like. It has a fixed part of 40 bytes. It has less header fields, and it has source address and destination address that are 128 bits long. We then have optional extension headers, that means 0 or more, and then we have the variable length of data. If you look at the header fields, we have the version, which obviously holds the value of 6. We have bits for the traffic class, which is similar to the type of service bits in the IPv4. Only that in addition to that, we have a flow label, which together with the source address can distinguish packets that need a specific kind of servicing on its way. There is a header field called hop limit, which identifies the maximum number of intermediary nodes, where each node will decrement this value by 1, regardless of the time until the packet is forwarded. So this is, in a sense, different from time to live in IPv4, which covers both timing and the number of hops. In the IPv6, it's only the hop limit. Time is eliminated from here, and the application will need to actually take this in account. Next header is a number out of the list of IP protocol numbers that identifies the next header or the next layer protocol. It depends. If we have optional extension headers, then the next header will point to the first optional extension header. If there are no optional extension headers, then the next header will normally be something like TCP, UDP. The other fields are obvious: payload length, source address, and destination address. Optional extension headers are divided into these categories. We have headers with the hop-by-hop options. These means options that must be looked at and performed by each hop through which this packet goes through. We have routing headers, fragment headers, options that need to be considered by the destination only. And then we have the authentication header and the encapsulation security payload header, which are basically the IPsec. So having covered this generic stuff, before we move on and talk about more specific things, we need to actually realize that IPv4 and IPv6 are quite incompatible, which means that interworking and coexistence have lots of issues. There were some approaches like network address translation, protocol translation, and it has been deprecated because of some security issues. We have solutions like dual stack, we have tunneling, but these actually tend to complicate voice over IP deployments. And it turns out that our NetNet SD beats most of these issues. Now, the NetNet SD is none of the following. It is neither a firewall, nor a router, nor a proxy, not is it an ALG. It is something else. It is a back-to-back user agent, which in this context that we discuss is sort of an isolating element. The back-to-back user agent for a SIP originator is as a destination, and for the target, it is an originator. So one side of the NetNet SD can be attached to a whole cloud of IPv6 endpoints, and on the other side, the same SBC will be a member in an IPv4 network. And because the SBC is based on the back-to-back user agent application, we have that logical separation between these two clouds. And thanks to that, the SBC will translate, convert, tweak, and modify and change everything that's needed for the IPv4, IPv6 interoperation. IPv6 and Session Initiation Protocol. The basic SIP RFC 3261 simply says SIP works with both IPv4 and IPv6. SIP form and IPv6 forms have joined forces, and in 2010 there was a statement that you can see in front of you, a part of which I magnified. And it says that IPv6 syncs seamlessly with SIP in the application layer, which serves as the next generation signaling protocol for handling voice over IP and multimedia communications over IP networks. So it seems like ideal world. Not everything is always that ideal, and we have to look at the other sources of information. For instance, there is an RFC 6157 which addresses some IPv6 transition issues for the SIP. More specifically, proxy behavior and user agent behavior for both signaling and media. And it turns out that for many scenarios, the proxies must be dual stacked. That means they need to support at the same time IPv4 addresses as well as IPv6 addresses. Proxies, in addition to that, must stay involved in the entire dialogue, not just in the transaction. And the IPv6 user agent must directly or indirectly support IPv4 addresses for media. And this is best clarified by looking at this diagram. What we see here in the middle is a dual stack proxy. That means it is capable of IP version 4 and IP version 6. And on the sides, we can see an IP version 4 only SIP phone, and on the right-hand side, IP version 6 only. And a call is being established. We see the first invite going to the proxy, and the proxy translates it to IPv6. And because the proxy knows that it needs to stay in the dialogue, it actually adds record route headers to the invite. And these record route headers propagate all the way and all the way back, so that the endpoints use the proxy all the time. So in other words, the proxy stays within the dialogue. And that makes a lot of sense, because that proxy has an added value of translating between IPv6 and IPv4. And this is how we make sure that it stays throughout the whole call. This is very nice. The point is that that the proxy doesn't deal with media, because it is simply a signaling entity. And the media is actually left to the mercy of the two endpoints. One of them is IPv4, and the other one is IPv6 only. So the media cannot flow, unless, as the RFC recommends, the IPv6 only phone for media should support IPv4. So this is really a drawback, and this is simply something that we want to clean up, at least in voice over IP during the transition period. So let's take a look at the NetNetSD in the IPv6 environment. As a back-to-back user agent, IP version 6, IP version 4 interworking is greatly simplified for the customer. As I said a couple of minutes ago, the NetNetSD is not a firewall, it's not a router, it's not a proxy, it's not an ALG. It is a destination for the originators. It is an originator for the targets. And we have full isolation, including IP addressing, that is provided. Now, the SBC is ideally poised for the IPv6, as well as IPv6, IPv4 scenarios. And if you look at the illustrated example, the IPv6 endpoints are added to existing IPv4 endpoints, and at the same time, the carrier's IPv4 core network and agreement is not required to change. So that represents a huge cost saving and time saving, and once the IPv4 side migrates to IPv6, the migration is going to be very smooth. We can now talk a little more specifically about the IPv6 and the NetNetSD in terms of configuration and placing calls. We start with the initial IP version 6 configuration steps. They're all documented, and from the documentation one can learn that the steps would be: first, add the supporting license. If, you want IP version 4, IP version 6 into operation. You then edit the system config element so that the IPv6 support parameter is set to enabled. You then reboot, and then you proceed the exact same way you have configured the NetNetSD before. You only need to be aware to the fact that many of the configuration elements, some of which you can see at the bottom, like network interface, will have fields that will accept IPv6 addresses. Let's take a look at the sample, also simple, peering configuration or SIP trunking. We have an IPv6 peer realm, and we have an IPv4 core realm. We have a soft switch on the right-hand side, and let's say an enterprise PBX on the left-hand side. When we configure the NetNetSD for this deployment, we have to plug in the license so that IPv6 and IPv4 interworking will be included. In the system config, we have to enable the IPv6 support. We then create the network interfaces, one with IPv4 addresses, the other one on the left with the IPv6 addresses. We have the realms, and we have the SIP interfaces and the steering pools. And again, according to which realm it is, they will be configured with either IPv4 addresses or IPv6 addresses. Lastly, we have to throw in the local policies, peer to core and core to peer. So you see that the local policy, in this case, the one at the bottom, will have an IPv6 address. Let's take a look at some screen captures. Show features will show you all the licensed features, and as you can see at the bottom, you have IPv4 v6 interworking. In the system config element, close to the bottom, you will see IPv6 support enabled. The network interface element looks like this. The IP address is an IPv6 IP address, and there is no netmask. Instead, you can see /64, and /64 is a prefix that actually identifies the length of whatever is not the interface ID. So since interface ID is the last 64 bits, then /64 actually covers everything that is before that. And that will actually encompass in a globally routable address the site ID and the subnet. So the 64 is really the equivalent of a subnet mask. In this particular example, I also activated the HIP IP list with the same IP address and the ICMP address so that I can actually ping this interface using ping -6 on a PC. Let's take a look at the realm config element. In the realm config element, the variant at the top has address prefix which is not used. It's equivalent to the good old 0000. So here we see : : that means that we don't have any address prefix. In the bottom example, we have an address prefix which is like a globally routed IP address, /56. That means that the first 56 bytes that are marked in red will be sort of the subnet. Actually, what the 56 defines is all the CDXX subnets in the 2001 DB8:0 site. SIP interface, not much to discuss about it. The address in the SIP port will be an IP address. I'm sorry, an IPv6 address. All the rest remains the same. Same can be said about the steering pool. And in the local policy, you will see the IP version 6 address in the policy attribute. So you're looking at the local policy that routes from the core to the peer, where the peer is an IPv6 network. The peer realm is an IPv6 network, and the next hop has an IP address of version 6. Here is a call scenario. And we have a core realm here on the left-hand side. I drew this diagram so that it conforms with the flow capture. So normally we put the core on the right-hand side. This time it's on the left-hand side, and the peer realm is on the right-hand side. We have a call coming from a phone to a soft switch, then from a soft switch to the NetNet SD. And this is all IPv4, and you can see the invite right here. Okay, so it goes from one IPv4 address to the other IPv4 address. NetNet SD re-originates it, and you see the re-originated invite coming out of this SIP interface and going to that next hop, which are IPv6 addresses. One is here, and the other one is here. Here's a capture of the core side incoming invite, which is IP version 4 oriented. You can see the request line has invite SIP 172.16, etc. The VIA is IPv4. The contact is IPv4. And in the SDP body, the media IP address is IPv4. You look at the re-originated invite, and you see that it has been changed, or the original has been changed, so that the request line has the same phone number with the IPv6 address. The VIA of that re-originated invite is IPv6. The contact is IPv6. And the connection information now includes IPv6 address. Let's take a look at a mechanism which which needs to be understood in case of troubleshooting, and that's finding a node's MAC address. First of all, there are no layer 2 broadcasts like we use in the ARP. Instead of a layer 2 or Ethernet level broadcast, we use special layer 2 multicast, which is 3333FF, and then 3 more bytes that I will specify shortly. And again, you are looking at 6 bytes, and these bytes are actually a multicast address for layer 2. We don't use ARP because there is no ARP defined in IPv6. Instead, we use ICMP version 6 in order to resolve between an IPv6 address and the corresponding MAC address. So let's take a look at 2 nodes. One of them is an SBC, the other one is a PBX. They both have IPv6 addresses. Let's assume that the SBC knows, because it did this resolution before, the MAC address of the PBX. So an incoming invite can be re-originated and sent to the PBX. But now the PBX has the problem of sending back a response, like 100 trying or whatever, and it needs to know the MAC address of the NetNet SD. So what it does, it sends an ICMP v6 message, which is called neighbor solicitation, which is pretty much like saying I need a MAC address for FE80, A25FF, etc. In other words, the IPv6 address of the NetNet SBC. That message on layer 2 is sent to 3333FF, and then these 3 bytes are the last 3 bytes of the IP version 6 address. And this is this actually leads us to what we call the solicited node address. So the A1, B0, B3 are the last 3 bytes of the solicited node address that every host has to have it configured to the interface. Now, the SD's Ethernet device, or the layer 2 device, if you will, listens on this multicast address. It propagates up to the ICMP v6 entity in the software, and back comes an ICMP v6 reply, which is called neighbor advertisement, and it presents to the PBX the SBC's MAC address. And this is exactly when the PBX is able to send the response and the subsequent responses, and the 2 nodes can communicate because they have all that they need to know. Take a look at this screen capture. You can see an invite right above the highlighted frame. The highlighted frame is the neighbor solicitation message, which is required so that the PBX will be able to send a response. At the bottom, you can see the ICMP message, which has the type of neighbor solicitation, and the target address, which is the address for which the MAC address is needed, is shown here, FE80, A25FF, and so on. That's actually the NetNet SD address. If you look at the layer 3 packet, you can see the version 6 right here, and you can see all the other fields. But most importantly, you can see that the source address is the IPv6 address of the PBX, and the destination is the FF021, and then you see FF A1, B0, B3. This is exactly the neighbor solicitation address. If you look at the layer 2 packet, you can see that the destination is not a specific MAC address. It is a layer 2 multicast, which is 3333FF, and the last 3 bytes of the node solicitation address. The next frame, which is right here, is the neighbor advertisement, which is the response that carries the requested MAC address. Let's take a look at the sample access configuration. We have an access realm with endpoints on the left-hand side. We have a backbone realm with the soft switch and a registrar on the right-hand side. What you can see here is that the configuration is fairly similar in terms of stacking the elements. It's only that we have to activate the registration caching. We have to plug in the local policy for the access to the backbone routing, and the registration caching or registration cache entries will be used for routing from the backbone to the access. Nothing new here, except for the usage of IPv6 addresses. Now, what you see here is the access realm registration request, which is actually sent by a phone to the NetNet SD over IPv6 network. So you see the registry here. You see the phone number that we want to register. And we see the IP version 6 address in the contact header. So that goes to the SD. The SD re-originates it to the backbone realm, where the transmitted the register message has register, the same AOR, only that the contact includes 172.16.0.11, which is the IP4 address of the SIP interface. Other useful commands for troubleshooting and for monitoring is like the show neighbor table. Now, I said before that there is no ARP in IPv6, so there is no ARP table for IPv6. So the information of IPv6 addresses together with the MAC addresses is actually in a different structure somewhere. And if you want to see the currently assigned IP addresses and the corresponding MAC addresses, you can type show neighbor table, and you will see, for instance, an IP version 6 IP address that corresponds to this MAC address. Also easy is to show the IP connections by simply typing show IP connections. You will see the IP version 4 connections as well as the IP version 6 connections, which are at the bottom and they are highlighted. And you can see the local address and the foreign address and the connection status, like listen or established. You can use the show SIPD endpoint IP with a phone number if you want to see, in the case of access deployment, the registration cache entry. And what you see in green are all the IP version 6 addresses and the SD contact, which is the one that is used in the outgoing register request to the registrar, contains IPv4 address. So everything is visible, everything is as easily accessible as it used to be before. Let's take a look at some log samples. zipmessage.log, and you can see the peer-side incoming invite for a call. And you see that absolutely all the addresses here are IPv6 addresses, because that corresponds to that to the example where the peer side is IP version 6. In the same log, you can see the message that is sent out to the next hop, which is our PBX, or our soft switch rather. And again, you can see the request line has an IP version 4 address, so does the via and the contact and the IP addresses in the SDP body. For educational reasons, I have left the green IPv6 addresses, which are normally taken care of using HMRs or FQDNs, but unless these measures are taken, you can see the IP version 6 addresses right here. And if the dialog transparency is set to enabled, that IP version 6 leaks through that call ID header. But then again, if we need to hide this, then the dialog transparency should be set to disabled. We can see the core side return the 100 trying. Okay, that comes from our soft switch. You can see the core side return 200 OK. And eventually you can see the return 200 OK to the peer side. That means to the originating PBX at the enterprise. And then again, everything is back to IPv6 there. Another log that you can look at is the zipd.log, and you can see how the MBCD builds the media context and flows. Now, this is normally a fairly lengthy output, and I only show a small part of it. You can see add flow, which is an MBCD transaction, and for that transaction we have a reply, and we get the context number, and we see the destination and the sources for the media, which are the corresponding IP version 6 and IP version 4 addresses. Some questions that have been asked. I have a question here. Let's see. Can we ping via IPv6 by forcing out a specific realm/interface similar to IPv4? For instance, like ping 2115:C, etc., to verify network connectivity? The answer is simply yes. I got another question here, like, does an IPv6 address show up in the ARP table? No. There is another command called show neighbor tables, which is used instead. Somebody asked here, does the SD accept the condensed version of IPv6 address? Of course, it does. Somebody asked here, will the SD route header will the SD use route headers to route if it has a valid IPv6 address? And again, yes. Can the SD use both IPv4 and IPv6 route headers interworking for routing? And again, the answer is positive. Does the SD support IPv6 with the TLS? Yes, and that will be supported in version 6.3. Thank you.
that's the end of our presentation for today. That was great. Thank you so much, Mare. Later today, you'll receive a soft copy of these presentation materials along with a soft copy of all of the questions asked during the presentation. These questions contain some great points about today's topics. In summary, key points for today is that the transition to IPv6 is inevitable, and Acme Packet has the functionality to handle the changes. IPv6 interworking for multimedia traffic on the NetNet Session Director is simple and effective. Configuring the NetNet Session Director to support IPv6 interworking is done in the same manner as you would configure any other features. So there's no need to learn a different approach to configuration. And last, the NetNet Session Director will eliminate the headaches that the new IPv6 addressing scheme is going to introduce into your network. Some additional resources for you include the presentation materials that we will again be sending out a link to. They'll be hosted on acmepacket.com, and again we'll send out the link to everyone who attended today's presentation. You also could attend formal instructor-led